Space has no station movement, but in relation to the Milky Way, there are regions located above and below our solar system. These areas contain gas and dust clouds, old star clusters, dark matter halos, and small distant galaxies. Studying these regions helps scientists understand the structure and movement of our galaxy. By exploring from our local area to the outer parts of the Milky Way, we can identify not only stars and clouds, but also the invisible forces that shape the galaxy and link its different parts. Before we dive in, tell us where you're tuning in from. We love seeing how people from all over the world come together to explore the universe with us. And if space fascinates you as much as it does us, subscribe to help our community grow even larger. Our solar system is located within the great disk of the Milky Way galaxy, a vast, flattened region made up of stars, clouds of gas, and fine grains of cosmic dust. This enormous disk is the part of the galaxy that forms its well-known spiral shape, the one seen in telescopic images and artistic renderings. The disk itself is thin when compared to the overall size of the Milky Way, measuring about 1,000 light-years thick, but stretching more than 100,000 light-years across from one side to the other. It is like a giant cosmic pancake of stars, glowing nebulae, and dark interstellar clouds, turning slowly in the endless space of the galaxy. Inside this disk, our solar system occupies a modest but significant position. It lies in a small spiral arm called the Orion Cygnus arm, sometimes referred to as the Orion Spur. This arm is not one of the Milky Way's main spiral arms, such as the Sagittarius or Perseus arms, but rather a smaller branch between them. The Sun and its planets are located roughly halfway between the galactic center, the crowded, energetic heart of the Milky Way, and the outermost edge of the disk, where stars become more widely spaced and the density of material falls sharply. This intermediate position gives our solar system a kind of cosmic balance, placing it in a region that is neither too violent nor too empty. Closer to the galactic center, the environment becomes extremely active. There, stars are packed together at much higher densities, and powerful events such as supernova explosions, bursts of gamma rays, and intense radiation from the supermassive black hole known as Sagittarius A make the region hazardous for life as we know it. Farther toward the edge of the galaxy, the number of stars decreases, and the supply of gas and dust needed to form new stars and planets grows thin. But our solar system sits in a region where both conditions are moderated. It is far enough from the center to avoid the most dangerous radiation and gravitational disturbances, yet near enough to the galactic plane to share in the ongoing cycle of star birth and death that replenishes the interstellar medium. This location has likely played an important role in the stability and survival of Earth and the rest of our solar system. Being positioned halfway between the inner and outer parts of the galaxy has provided a relatively calm and safe cosmic neighborhood. The Sun orbits the galactic center at a comfortable distance, protected from the extreme gravitational forces and energetic explosions that occur more frequently in the crowded inner regions. At the same time, this position allows access to the gas, dust, and cosmic materials circulating through the Milky Way, which have subtly influenced the long-term evolution of the solar system and its surroundings. This balance could be seen as a kind of galactic Goldilocks zone, where conditions are not too harsh and not too barren, just right for maintaining long-term stability, and perhaps for the development of complex life. The Sun, along with the rest of the solar system, moves around the Milky Way in a vast orbit that is not a perfect circle, but a slightly elongated ellipse. One complete journey around the galaxy takes between 225 million and 250 million Earth years. This enormous time span is often called a galactic year, meaning that since the formation of the solar system about 4.5 billion years ago, the Sun has completed only about 20 galactic orbits. As it travels, the solar system does not move in a flat, unchanging path. Instead, it follows a gentle wave-like motion, oscillating up and down through the galactic plane. Over tens of millions of years, it drifts above the plane of the Milky Way and then slowly falls back below it, tracing a slow, rhythmic path through space. This vertical motion is not just a curiosity, it has important effects. As the solar system moves through different regions of the galaxy, it encounters zones with varying densities of stars, clouds of gas, and concentrations of cosmic rays. Passing through these environments may influence many processes, such as the number of comets entering the inner solar system, the level of cosmic radiation reaching Earth, and even the long-term climate and biological conditions on our planet. The gravitational pull from the dense regions can also affect the outer parts of the solar system, disturbing distant icy bodies and sending some of them inward as comets. Over time, this slow movement through the Milky Way helps mix and redistribute interstellar material, maintaining the galaxy's dynamic and ever-changing nature. Our solar system's position also shapes how we view the galaxy from Earth. When we look into the night sky, the Milky Way appears as a bright misty band stretching across the heavens. This is the view along the galactic plane, the densely populated region filled with stars, nebulae and clusters. But if we look directly above or below that band, we're gazing out of the galactic disk into the more sparsely populated halo, a vast region surrounding the Milky Way that contains old, dim stars, globular clusters, and invisible structures of dark matter. These directions, above and below the disk, help astronomers study the vertical structure of the galaxy and understand how matter is distributed from the dense plane outward into the thin, ghostly halo that encloses the Milky Way. The concept of above and below becomes meaningful only in relation to the galactic plane. In space itself, there is no universal up or down, but within the framework of the Milky Way, the disk serves as a natural reference point. By studying the movement of stars and gas both within and beyond the plane, scientists gain insight into how the galaxy formed, how it maintains its spiral structure, and how it evolves over billions of years. The position of our solar system, therefore, provides not only a stable home, but also a privileged observational platform for exploring the larger structure of our galactic environment. Understanding where we are in the Milky Way is also essential for understanding the boundaries of our solar system itself. Many people think of the solar system as the region containing the Sun and its 8 planets, but its true extent reaches far beyond the orbit of Neptune, the outermost major planet. The Sun's influence extends into a vast and complex region, where its magnetic field and streams of charged particles, known as the solar wind, interact with the interstellar medium, the thin, diffuse gas that fills the space between the stars. The first major boundary in this region is the heliosphere, an enormous bubble formed by the continuous outflow of the solar wind. The Sun constantly emits streams of charged particles, mostly electrons and protons, that spread outward in all directions. These particles carry with them the Sun's magnetic field, creating a gigantic shield that envelops the planets and pushes back the flow of high-energy cosmic rays that come from the rest of the galaxy. The heliosphere is not a perfect sphere. It is somewhat flattened and elongated because the solar system itself moves through the interstellar medium at high speed. In a way, the heliosphere acts like the bow wave of a ship moving through water, shaped by the interaction between the solar wind and the surrounding interstellar gas. This vast bubble extends for billions of kilometers from the Sun, marking the first major limit of our solar system's space environment. But the heliosphere does not have a sharp edge. Instead, it transitions gradually through several layers. The first of these is the termination shock, where the solar wind slows down abruptly after traveling supersonically through space. At this point, the flow of solar particles collides with the interstellar medium, losing much of its speed and creating a turbulent boundary region. This region is filled with energetic particles, magnetic turbulence, and complex plasma interactions. Beyond this lies the heliopause, the outermost boundary of the heliosphere, where the pressure of the solar wind is finally balanced by the opposing pressure of the interstellar medium. Beyond the heliopause, the Sun's influence fades, and the interstellar environment takes over. This is the true frontier between the solar system and the rest of the galaxy. The heliopause marks the point where interstellar space begins. In recent decades, this boundary has been crossed by 2 human-made spacecraft, Voyager 1 and Voyager 2, launched in the late 1970s. After travelling for more than 40 years, these spacecraft have now entered interstellar space, becoming humanity's first messengers to leave the protective bubble of the Sun's influence. Their instruments continue to send back data about the temperature, density, and magnetic conditions of this new environment, giving us our first direct look at the space between the stars. These measurements have confirmed that the transition between the heliosphere and interstellar space is not sudden but gradual and constantly shifting, influenced by changes in the solar wind and the surrounding galactic medium. Even farther beyond the heliosphere lies one of the most mysterious regions of all, the Oort cloud. Named after the Dutch astronomer Jan Oort, who proposed its existence in the mid-20th century, The Oort cloud is believed to be a vast spherical shell of icy bodies surrounding the solar system at enormous distances, up to 100,000 astronomical units from the Sun, or nearly 2 light-years away. 1 astronomical unit is the average distance between the Earth and the Sun, about 150 million kilometres, so the scale of the Oort cloud is almost beyond comprehension. Although no direct observations have yet confirmed its existence, its presence is strongly supported by the behaviour of long-period comets, which appear to come from very distant and randomly oriented directions. The objects in the Oort cloud are thought to be remnants of the early solar system, icy planetesimals that were scattered outward by the gravitational influence of the giant planets billions of years ago. Over time, they formed a vast, diffuse shell surrounding the Sun. Every so often, the gravitational pull of nearby stars or the tidal forces of the Milky Way disturb these icy bodies, sending a few of them inward toward the Sun. As they fall closer, the heat of the Sun causes their icy surfaces to vaporize, producing the glowing tails that make comets visible in the night sky. The Oort cloud, therefore, represents both a distant boundary and a potential source of new activity within the solar system. Because of its spherical shape, the Oort cloud is not limited to the plane of the Milky Way. It extends above, below, and all around, forming a kind of ghostly sphere that blends the solar system into the larger structure of the galaxy. Beyond it lies truly interstellar space, a realm where the Sun's gravity becomes too weak to dominate, and where the forces of the galaxy as a whole begin to take over. This makes the Oort cloud a natural transition zone between the local environment of our solar system and the broader cosmic surroundings. It is the last region that can be said to belong to the Sun before the influence of the galaxy becomes stronger. Understanding these outer boundaries is essential, because they show that the solar system is not isolated. It is part of a much larger and more complex system of interactions between the Sun, the interstellar medium, and the gravitational and magnetic forces of the Milky Way. The Sun's influence does not end abruptly, but fades gradually across billions of kilometres, blending smoothly into the galaxy's broader environment. The heliosphere, termination shock, heliopause, and Oort cloud together form what might be called the solar system's outer cocoon, a protective envelope that shields the inner planets from the harshest effects of galactic radiation, while still allowing exchanges of matter and energy with the wider universe. These boundaries are not fixed or unchanging. The size and shape of the heliosphere, for instance, depend on the strength of the solar wind, which varies with the Sun's 11-year activity cycle. When solar activity increases, the solar wind becomes stronger, expanding the heliosphere and pushing its boundary farther outward. When the Sun is quiet, the heliosphere contracts slightly, allowing more cosmic rays from the galaxy to penetrate the inner solar system. Similarly, the shape of the Oort cloud is influenced by passing stars, interstellar clouds, and the overall gravitational field of the Milky Way. Over millions of years, these influences can slightly distort the cloud, causing slow shifts in its structure and density. Even our solar system's journey through the Milky Way affects these distant regions. As the Sun moves through areas of different interstellar density, the external pressure on the heliosphere changes, causing it to expand or compress. Some astronomers think that when the solar system passes through dense interstellar clouds, the heliosphere may shrink dramatically, reducing its protective ability and allowing higher levels of cosmic radiation to reach Earth and the other planets. Such events could have played a role in the planet's past climate changes or even in biological evolution. All of these processes remind us that space, even on the scale of our solar system, is not static but dynamic and interconnected. The Sun, planets, and distant icy bodies are all parts of a larger galactic ecosystem, constantly shaped by forces both internal and external. Our solar system is not just a family of planets orbiting a single star. It is a mobile, evolving structure travelling through a complex galaxy filled with magnetic fields, cosmic rays, and interstellar matter. Seen from this larger perspective, our position within the Milky Way takes on even greater meaning. The solar system's safe, middle ground location within the Orion Cygnus arm provides both stability and connection. It shields us from the dangers of the galactic core while keeping us in touch with the rich materials of the star-forming regions that make life and planetary evolution possible. As the Sun and its planets continue their long orbit around the galactic centre, they carry with them the memory of countless cosmic encounters, supernova remnants, passing stars, waves of interstellar dust, and invisible tides of dark matter that shape the galaxy's gravitational landscape. Understanding where we are in the Milky Way and how far the Sun's influence extends gives us more than just a map of our cosmic address. It reveals how deeply everything in the universe is connected. From the glowing stars of the galactic plane to the frozen bodies of the Oort cloud, from the turbulent edge of the heliosphere to the quiet vastness of interstellar space, every part of our surroundings is linked by gravity, magnetism, and motion. Our solar system, balanced between the galactic center and the outer rim, is part of an ongoing story that spans billions of years and reaches far above and below the plane of the Milky Way. It is a reminder that even here, within the calm of our planetary neighborhood, we are passengers on a journey through one of the most magnificent structures in the universe. The galactic plane is the great foundation and central structure of our home galaxy, the Milky Way. It is not just a simple layer of stars, it is an enormous, thin and wide disk made up of countless stars, immense clouds of gas, and fine grains of cosmic dust spread across space. This vast disk is the feature that gives our galaxy its famous spiral shape, with magnificent arms that extend outward in graceful curves from the tightly packed galactic center. The galactic plane is the true heart of the Milky Way's activity, and the stage on which most of the visible life of our galaxy unfolds. Within this flattened disk lies almost everything we can see when we look at our galaxy through telescopes. Young stars burning bright, glowing regions where new stars are born, and large open clusters that contain hundreds or even thousands of suns bound together by gravity. The galactic plane is, in every sense, the living, breathing layer of our cosmic home where the greatest amount of energy, motion, and creation takes place. From our point of view on Earth, when we look toward this plane, we see it as a glowing, milky ribbon of light stretching across the dark night sky. That faint band of radiance, which appears like a cloud, but is actually made of billions of distant stars packed together, is what gave our galaxy its name, the Milky Way. Every star that makes up that glowing band belongs to this grand galactic disk, and our own sun is one of them. Our solar system itself is deeply embedded within this immense and delicate plane. It follows a nearly circular orbit around the galactic center, travelling through this star-filled region over the course of hundreds of millions of years. But this motion is not as simple as circling a central point. Our solar system's journey through the galaxy is complex and dynamic. As it moves along the plane, it interacts gravitationally with nearby stars, immense molecular clouds of gas, and even the mysterious and invisible dark matter that surrounds and threads through the galaxy. These interactions constantly shape and influence our system's motion, nudging it gently over long stretches of time. The galactic plane itself is astonishingly flat compared to the galaxy's full vertical size. Most of the stars, gas and dust are tightly concentrated within this thin disk, while much less matter exists far above or below it. Because of this, the galactic plane acts like a kind of cosmic equator, an imaginary dividing line that defines what astronomers call above and below, in the context of the Milky Way. These directions are not absolute in space, but are instead measured relative to this great flat structure. However, the galactic plane is not a static or motionless surface. It is alive with activity and change. As our solar system continues its long orbit around the Milky Way's core, it passes through regions of differing density and composition, some crowded with stars and gas, others more empty and dark. Along the way, it encounters bright star clusters, dense interstellar clouds, and occasionally the gravitational influences of passing stars that slightly alter its course. These continual interactions help shape the distribution of stars and gas within the plane, and even play a role in the birth of new stars over time. In contrast, the regions found above and below the plane are quieter and less crowded. They are populated mostly by older stars that have drifted away from the denser central disk. Here, matter is more scattered, and the galactic environment is thinner and calmer. This sharp difference between the active, crowded plane and the quiet, diffuse regions above and below gives the Milky Way its layered, three-dimensional structure. Studying the galactic plane helps astronomers understand this structure in greater detail. It serves as the baseline for mapping how the galaxy's material, stars, gas, dust, and even dark matter, is arranged vertically. By observing how these layers extend above and below the plane, scientists can trace the full shape and composition of the Milky Way, uncovering how gravity, star formation, and galactic evolution are all connected. Even though it might seem that our solar system moves smoothly and evenly along a flat path within this plane, its true motion is more intricate. In reality, the solar system performs a slow, graceful, wave-like movement above and below the plane, an effect known as vertical oscillation. This oscillation is caused by the gravitational pull of the dense matter within the galactic disk. The immense gravity of stars, gas clouds, and dark matter gently tugs on the solar system as it travels, causing it to rise slightly above the plane, then sink below it again over time. This vertical motion is incredibly slow and steady. It takes tens of millions of years to complete just one cycle. Each full oscillation, in which the solar system moves from below the plane to above and back again, takes roughly 60 to 70 million years. Over the course of that time, the solar system reaches a maximum height above the plane, then gradually falls downward, crossing through the dense central layer before continuing to the opposite side. This cycle repeats continuously, like a cosmic heartbeat. The motion is smooth, not violent or chaotic. It resembles a soft, three-dimensional wave that the solar system rides as it orbits the galactic center. The galactic plane acts as the middle balance point of this motion, the line of equilibrium that the solar system crosses every few tens of millions of years. In this way, our solar system does not simply orbit the galaxy in a flat circle, but moves in a gentle up and down rhythm, as if breathing along with the Milky Way itself. This oscillation can be compared to a kind of galactic season. Just as the Earth experiences cycles of spring, summer, autumn, and winter as it orbits the Sun, the solar system experiences vast galactic seasons as it moves through different layers of the Milky Way. When it passes through the denser regions of the galactic plane, the Sun and planets encounter thicker concentrations of interstellar gas and dust. During these times, the solar system might be exposed to slightly higher levels of cosmic rays or face subtle gravitational influences that could disturb the distant cloud of icy bodies known as the Oort cloud, possibly sending some comets inward toward the inner solar system. On the other hand, when the solar system drifts farther above or below the galactic plane, it enters regions that are much less dense. In these zones, there is less gas, dust, and interstellar material overall, making the environment calmer and clearer. The surrounding space becomes more empty and less turbulent, offering a quieter cosmic neighborhood. This means that the solar system's local environment, what surrounds us on the scale of light years, is constantly changing as we move through the galaxy. These gradual oscillations show that our solar system is not fixed or stationary within the Milky Way. It is an active participant in the galaxy's dynamic structure, forever moving and interacting with the forces and matter around it in 3 dimensions. The neighborhood of stars and gas around us is never the same for long. It shifts over millions of years as we rise and fall through the galactic layers. The concept of vertical oscillation also gives astronomers a clearer understanding of what above and below mean when describing our galaxy. These directions are defined by the galactic plane itself, with above referring to one side of the plane and below to the opposite side. The movement of the solar system through these directions helps scientists study how stars, gas clouds, and dark matter are arranged in relation to our position. It allows them to build a 3-dimensional picture of the Milky Way, showing not just the flat spiral shape of the disk, but also its vertical thickness and structure. Over millions of years, this gentle bobbing motion affects how the solar system experiences its galactic environment. When passing through the plane, we move through regions that are richer in material and energy. When farther away, we drift through quieter and thinner space. Although these changes are so slow that no human could ever notice them within a lifetime, they play an essential role in shaping the long-term evolution of both the galaxy and our place within it. This motion also reminds us that nothing in the universe is truly still. Every star, every cloud of gas, and every system of planets is in constant motion, bound together by the invisible threads of gravity. Even something as vast as the Milky Way is not rigid or unmoving. It pulses, rotates, and shifts over time. The solar system's oscillation through the galactic plane is one small part of this grand cosmic dance, an echo of the endless motion that defines the universe itself. The galactic plane, therefore, is much more than just a flat layer of stars. It is the very heart of the Milky Way. the arena where stars are born and die, where clouds of gas and dust swirl together under gravity to form new worlds, and where the intricate balance of forces gives shape to everything we see in the night sky. Our own sun and planet are participants in this vast cosmic system, carried along by the same gravitational rhythms that move billions of other stars. As the solar system drifts gently above and below this immense galactic disk, it takes part in the ongoing story of our galaxy's evolution. Over tens of millions of years, it travels through changing cosmic landscapes, through denser and thinner regions, through zones of creation and calm. Every movement, whether around the galactic center or across the galactic plane, reveals a universe that is alive with motion and energy, on scales far beyond human imagination. The galactic plane is both our home and our map within the Milky Way. It defines the structure of our galaxy, guides our sense of direction in space, and connects us to the billions of stars that share this vast rotating disk. The region that lies above the galactic plane of the Milky Way marks a gradual transition from the crowded, star-filled midsection of our galaxy into areas where the stars, gas, and dust become less densely packed. Yet even here, the influence of the thin disk, the main structure that dominates much of the Milky Way, remains strong. This thin disk stretches several hundred light-years above the central plane and serves as one of the most active and vital regions of the entire galaxy. It is within this extended, flattened layer that most of the Milky Way's stars, gas, and planetary systems are born. It contains the bright and youthful stellar populations that give our galaxy its living, dynamic character. Many of these stars share similarities with our own Sun, and their study allows astronomers to understand how solar systems form, evolve, and distribute across the galaxy. In cosmic terms, the stars of the thin disk are considered relatively young. Most are less than 10 billion years old, a period that represents only part of the Milky Way's long and complex life. These stars display a wide range of spectral types, meaning they vary greatly in temperature, colour, and mass. Among them are massive hot blue giants that shine with fierce intensity, as well as more modest yellow dwarfs like our Sun, which sustain stable light and heat over billions of years. The thin disk's youth and continued activity make it one of the galaxy's most vibrant regions, constantly renewing itself through star formation. Because new stars continue to form here, the thin disk is filled with open clusters, groups of stars that were born together from the same giant cloud of molecular gas. These clusters remain loosely connected by gravity, slowly drifting apart over time but still sharing similar compositions and ages. Astronomers regard these clusters as natural laboratories. By observing them, scientists can trace how stars evolve from infancy to maturity, how elements are created within stellar cores, and how these materials enrich the galaxy. The open clusters also reveal valuable clues about the formation of planetary systems, since many of their stars possess disks of gas and dust capable of forming planets. Although the thin disk dominates the structure above the galactic plane, it is surprisingly flat. Compared to the vast vertical thickness of the Milky Way's surrounding halo, the thin disk appears like a delicate sheet of light. Yet even within its flattened form, it still stretches hundreds of light-years above and below the central plane. This makes it larger than the immediate area around our Sun, but smaller than the thick disk or the extended halo that envelops the galaxy. Within the thin disk, billions of stars fill the space above our solar system. However, their apparent density decreases as one moves farther from the galactic plane. In other words, stars become less numerous with height, creating a gradual thinning that defines the upper boundaries of the disk. Most of the galaxy's stars are concentrated near the mid-plane, but the region above us remains an important zone that contributes significantly to the Milky Way's overall structure. The thin disk above our solar system holds special significance because it contains many stars rich in heavier elements, those created through the nuclear processes of earlier generations of stars. In astronomy, all elements heavier than hydrogen and helium are called metals, though they include everything from oxygen and carbon to iron and silicon. These metals are crucial for the formation of solid planets, atmospheres, and, potentially, life itself. Stars in the thin disk tend to have higher metallicity compared to older populations in the thick disk and halo. This indicates that the thin disk is a region shaped by the recycling of stellar material through many cycles of birth, death, and renewal. Alongside the stars, the thin disk contains enormous amounts of interstellar gas and dust. These components make up what astronomers call the interstellar medium, the raw material from which new stars and planets emerge. Far from being an empty void, the space above the galactic plane is filled with vast clouds of hydrogen and helium, mixed with small traces of carbon, nitrogen, oxygen, and other heavier elements. Within these clouds, gravity can cause certain regions to collapse, leading to the formation of new stars. Because the gas density in the thin disk remains high enough for such collapses to occur, this region is the galaxy's most active site for starbirth. The interplay of gravity, turbulence, and radiation shapes these molecular clouds, producing intricate structures that often glow brightly in infrared and radio wavelengths. Observations of the thin disk above our solar system provide astronomers with a unique opportunity to study the Milky Way's dynamics, how it rotates, how its stars move, and how its spiral arms evolve. Stars in this region generally follow nearly circular paths around the galactic centre, moving in the same general direction as our Sun. This orderly motion helps maintain the disk's coherent, flattened shape. Yet small deviations occur over millions of years, as stars migrate inward or outward due to gravitational interactions with other stars, gas clouds, or the spiral arms themselves. These subtle shifts slowly change the composition of different regions within the disk, creating a constantly evolving environment. Our solar system's position within the thin disk also means that it experiences various cosmic events originating above and around it. One of the most powerful of these events is the supernova, the explosive death of a massive star. Supernovae occur regularly within the thin disk, each releasing enormous amounts of energy, high-speed particles, and freshly forged heavy elements into space. These explosions play a crucial role in the galactic ecosystem. They enrich the interstellar medium with metals, provide shock waves that can trigger new rounds of star formation, and sometimes even alter the orbits of nearby stars through gravitational disturbances. The thin disk is thus a constantly active environment, where destruction and creation go hand in hand, shaping the evolution of the Milky Way. Many of the stars within the thin disk also host exoplanetary systems. In recent decades, astronomers have discovered thousands of such systems throughout the galaxy, and a large proportion of them belong to the thin disk. Because these stars often share chemical properties with our Sun, they are prime candidates for the existence of planets similar to Earth. This makes the region above the solar system particularly interesting for astrobiology, the study of life's potential beyond our planet. The abundance of metals and stable, long-lived stars increases the chances of rocky planets with atmospheres and liquid water, essential conditions for life as we understand it. In this sense, the thin disk above us may contain numerous worlds that mirror our own, orbiting distant suns scattered across the galactic sky. Structurally, the thin disk is far from uniform. It contains intricate substructures that reveal its dynamic history. Among these are the spiral arms, vast curving lanes of stars and gas that wind outward from the galactic centre. These arms are not solid features but regions where density waves compress gas and trigger bursts of star formation. Between the arms, there are quieter stretches where older stars dominate. Embedded within the disk are also stellar streams, rivers of stars that move together through space, often the remnants of smaller galaxies that merged with the Milky Way billions of years ago. The thin disk also bears the scars of these ancient collisions, with pockets of stars that preserve the memory of long-vanished galactic neighbours. By studying the stars above the galactic plane, astronomers can trace the Milky Way's rotation curve, which describes how fast different parts of the galaxy spin. This data helps scientists measure the distribution of mass, including both visible matter like stars and gas, and the invisible dark matter that exerts gravitational influence but emits no light. Observing the vertical motion of stars above the plane also provides clues about the gravitational pull of the entire galaxy, and how our solar system oscillates up and down through the disk over millions of years. Together, these studies reveal a complex three-dimensional picture of the Milky Way's structure and evolution. As one travels farther above the galactic plane, the thin disk gradually transitions into the thick disk, a region filled with older, more widely scattered stars. The boundary between the two is not sharp, but rather a gradual blending, where young, metal-rich stars give way to ancient, metal-poor ones. Yet directly above our solar system, the thin disk still dominates. Here, Relatively young stars and active star-forming regions continue to shine, making this layer the most dynamic and influential part of the Milky Way's vertical structure. The thin disk represents the present generation of the galaxy's life cycle, a realm of ongoing change where the forces of gravity, radiation, and chemistry continually interact to create new worlds. Although it might seem immense, the thin disk is actually quite narrow when compared to the galaxy's total height. This slenderness emphasizes the delicate balance that defines our solar system's position within the Milky Way. We reside in a layered environment where gravity binds everything together, yet motion and evolution constantly reshape the surroundings. Above our heads, stars orbit in great circles, gas clouds drift and collapse, and light from distant clusters travels for centuries before reaching our eyes. It is a neighborhood both fragile and magnificent, held together by the invisible threads of galactic dynamics. Studying the thin disk has practical benefits beyond theoretical understanding. When astronomers map the Milky Way using visible light, infrared radiation, or other wavelengths, the thin disk stands out as one of the brightest regions, second only to the galactic center. Infrared observations are particularly valuable because they can pierce through the dense dust clouds that obscure visible light, revealing hidden populations of stars and the complex web of interstellar gas above the plane. By observing these stars, scientists can measure star formation rates, estimate the ages of different stellar groups, and track the motion of matter through the galaxy. This information helps build a comprehensive model of how the Milky Way evolves over cosmic time. In the thin disk, every element of the cosmic cycle is visible. Stars are born from gas clouds, live for millions or billions of years, and eventually return their material to space through stellar winds or explosions. That recycled material becomes the seed for new generations of stars and planets. The process repeats endlessly, each cycle adding more complexity and richness to the galactic environment. The thin disk above the solar system embodies this ongoing renewal, a vast, glowing workshop of creation that has persisted for countless ages. Astronomers have found that the thin disk of stars vary not only in age but also in motion and chemical makeup. Some stars move in near-perfect circles, while others display slight tilts or vertical oscillations. These differences reveal past events that stirred the galactic disk, such as the passage of satellite galaxies or waves of star formation that rippled outward through the spiral arms. The chemical patterns recorded in the thin disk of stars also tell the story of the Milky Way's growth. Younger stars contain more heavy elements, showing that each generation builds upon the ashes of the last. By comparing the metallicities of stars at different heights above the plane, scientists can reconstruct how the galaxy enriched itself over billions of years. The region above the galactic plane also offers a window into the Milky Way's gravitational behavior. Stars and gas clouds are not fixed in place. They move in response to the combined pull of all the galaxy's mass. Our solar system, for instance, slowly oscillates above and below the galactic midplane in a cycle that lasts tens of millions of years. During this motion, it passes through regions of varying density, experiencing subtle changes in the gravitational field. These oscillations may even influence the flow of comets in the outer solar system by disturbing the Oort cloud, hinting at the deep connection between the galaxy's structure and our own local environment. Above the plane, astronomers also detect faint traces of high-energy radiation, supernova remnants, and interstellar bubbles carved out by massive stars. These phenomena contribute to the thin disk's dynamic appearance. They heat the surrounding gas, drive shock waves through the interstellar medium, and sometimes create superbubbles, enormous cavities filled with hot plasma that can extend for hundreds of light years. These structures mark the footprints of past generations of massive stars whose deaths helped sculpt the disk we observe today. From an observational standpoint, the thin disk provides one of the richest sources of data in the entire sky. When telescopes scan the heavens, the concentrated starlight of the thin disk forms the luminous band we call the Milky Way, visible to the naked eye on a clear night. Through telescopes sensitive to radio waves or infrared light, this band reveals hidden details, networks of gas filaments, dark dust lanes, and glowing nebulae where stars are being born. Each observation adds another piece to the puzzle of how the galaxy maintains its balance between order and chaos, between collapse and expansion, between destruction and creation. The study of the thin disk also sheds light on the future of the Milky Way. Over billions of years, The ongoing processes within this layer will continue to shape the galaxy's evolution. Stars will form, live and die, spiral arms will drift and reorganize, and gravitational interactions will subtly rearrange the stellar populations. Understanding the thin disk is thus key to predicting how the Milky Way will look in the distant future and how our solar system fits into that grand design. Ultimately, the thin disk above the galactic plane is much more than just a region of stars. It is a living system, constantly changing, constantly renewing itself. It contains the materials for planets, the ingredients for life, and the history of countless cosmic events. Every star above us carries within it the story of generations of explosions, mergers, and births that came before. Every atom of iron or carbon in our bodies was once forged in a star like those that now shine in the thin disk. In this sense, studying the region above the galactic plane is not merely an act of astronomy, it is a way of understanding our own cosmic heritage. The thin disk represents the Milky Way's beating heart, where gravity, radiation, and chemistry combine to produce the brilliant diversity of stars and worlds that populate our galaxy. From its rich clusters and spiral arms to its calm interstellar voids, it forms a continuous, interconnected system that links the smallest grains of dust to the largest stellar giants. Above our solar system, this region continues to glow with activity, carrying forward the timeless process of creation that has defined the Milky Way since its earliest days. Through careful study of its stars, gas, and motion, humanity gains not only knowledge of the galaxy's structure, but also a deeper appreciation of the cosmic environment that gave rise to us. The thin disk above the galactic plane stands as a shining testament to the dynamic life of our galaxy. It bridges the familiar world of the solar system with the vast expanse of interstellar space, connecting our local neighborhood to the grand cosmic story unfolding across billions of light years. Within its layered structure lie the clues to the Milky Way's past, the forces shaping its present, and the seeds of its future, an eternal dance of matter and energy that continues to unfold above and around us. Beneath the galactic plane of the Milky Way, the structure of our galaxy changes gradually but significantly, shifting from the young, bright and bustling regions of the thin disk into the older, quieter, and more dispersed territory known as the thick disk. This lower layer of the galaxy is not as crowded or as active as the thin disk that lies above the plane, but it possesses a deep and ancient history that stretches back almost to the time when the Milky Way itself was first forming. While the thin disk, the region that holds our own solar system, is filled with relatively young stars, glowing nebulae, and zones where new stars are still being born from clouds of interstellar gas and dust. The thick disk represents a much older chapter in the galaxy's story. Here the stars are ancient, their light dim and steady rather than brilliant and blue. Most of these stars have ages ranging between about 8 and 12 billion years, meaning that they were formed during a very early stage in the Milky Way's evolution, long before our Sun or Earth even existed. The thick disk extends much farther vertically than the thin disk, rising and falling thousands of light years above and below the galactic plane. Its stars are spread out more thinly, creating a region with a lower density of visible light. Instead of the dense, bright lanes of stars that dominate the thin disk, this lower region appears faint and diffuse, like a ghostly extension of the galaxy's main body. But though it might look dim and quiet, the thick disk holds some of the most important clues about the Milky Way's early life. The stars within it are living fossils, carrying in their chemical composition and motion the record of how the galaxy first came together from smaller fragments of matter and gas. Their atmospheres preserve traces of the materials that were available at the time of their birth, which in turn reveal the processes that took place during the Milky Way's infancy. Unlike the thin disk, where most stars move in nearly circular paths around the galactic centre, the stars in the thick disk follow more chaotic orbits. Their paths are more elliptical, and they tilt at various angles compared to the plane of the galaxy. This gives the thick disk its puffed-up appearance, as stars wander higher or lower above and below the main galactic plane. Their greater velocity dispersion, meaning their wider range of speeds and directions, suggests that they were either formed in a more turbulent period or were stirred up later by gravitational encounters. Many astronomers believe that ancient mergers with smaller galaxies, long absorbed by the Milky Way, played a key role in shaping this structure. When these smaller systems collided with our galaxy billions of years ago, Their gravitational pull likely jostled existing stars and mixed populations, leading to the thicker, more diffuse layer that we observe today. The stars in the thick disk tend to be less massive, fainter, and redder than those found in the thin disk. Many are red dwarfs, small, cool stars that burn their fuel slowly and can live for hundreds of billions of years. Others are white dwarfs, the remnants of stars that once shone brightly but have since exhausted their hydrogen fuel and collapsed into dense, Earth-sized cores. Some are subgiants and red giants, older stars in transitional stages of their life cycle, glowing dimly as they near the end of their evolution. Compared to the brilliant blue-white stars of the thin disk, these older stars emit a softer and redder light, giving the thick disk a fainter appearance when viewed through telescopes. A key difference between the two disks lies in their metallicity, the abundance of elements heavier than hydrogen and helium. Thick disk stars generally have low metallicity, meaning that they contain fewer heavy elements such as iron, carbon, or oxygen. This reflects the time period in which they formed, long before successive generations of supernovae had enriched the interstellar medium with these heavier elements. In the early universe, stars were born mostly from pristine hydrogen and helium left over from the Big Bang. As the first generations of stars lived and died, they created and released heavier elements into space. Younger stars like our Sun were formed from this recycled material, giving them higher metallicities. But the thick disker's low-metal stars are relics of an earlier era, preserving a record of a time when the Milky Way was still assembling itself from primordial matter. By studying the chemical makeup and motion of these ancient stars, astronomers can piece together the Milky Way's complex history. Each thick disk star acts like a time capsule, holding evidence of the conditions under which it formed. The patterns in their chemical elements, ratios of metals, isotopes, and lighter gases, allow scientists to trace which types of stars exploded nearby when they were born, and how much material those explosions contributed to their environment. Similarly, their movements across the sky reveal information about the galaxy's gravitational field, its total mass, and the distribution of both visible and invisible matter. Because the orbits of thick disk stars extend far above and below the galactic plane, their paths are strongly influenced by the overall shape of the Milky Way's gravitational potential, including the unseen dark matter halo that envelops the galaxy. Tracking these motions helps astronomers estimate how much dark matter exists and how it is distributed throughout the Milky Way. The thick disk is not simply a silent relic left behind from the past. It continues to interact dynamically with the other parts of the galaxy. Gravitational forces connect it to both the thin disk above and the halo beyond. Stars from the thick disk occasionally pass through the galactic plane, entering the thin disk's territory and mingling with its younger populations. In the same way, some thin disk stars can be scattered into higher orbits, temporarily joining the thick disk region. This constant exchange of stars and material shows that the Milky Way is far from static. It is a living, evolving system in which different layers influence one another. These vertical interactions help maintain the stability of the galactic structure, while also driving its slow transformation over billions of years. Because the thick disk's stars are older, many of them have already burned through much of their hydrogen fuel. A large number have evolved into red giants, swollen cooler stars that have expanded in size and brightness as their cores fuse heavier elements. Others have become subgiants or collapsed into white dwarfs. Despite their dimness compared to the hot young stars above, these aging stars are incredibly valuable to astronomers. Their ancient ages make them ideal for tracing the earliest phases of the Milky Way's development. Though they contribute less to the galaxy's visible light, they vastly outnumber the luminous young stars of the thin disk, especially when counted across the thick disk's immense vertical extent. This difference creates a layered visual effect when the Milky Way is observed from Earth or modelled in simulations. The upper regions of the galaxy glow brightly, filled with youthful, active stars forming within spiral arms, while beneath the plane lies a quieter, more subdued layer of older stars stretching far into space. Together, these layers form a vertical gradient of age, brightness, and chemical richness, a living cross-section of galactic evolution preserved in light and motion. The thick disk stands as a record of the Milky Way's transformation from a primitive gas-rich system into the majestic spiral galaxy we see today. Further below, the thick disk begins to blend into the halo, a nearly spherical region surrounding the entire galaxy. Some thick disk stars with their wide orbits bridge the space between these two zones. Within this transition area, astronomers have found remnants of past galactic mergers, streams of stars moving together through space, sharing common origins. These streams are the debris of smaller galaxies that were captured and assimilated by the Milky Way long ago. Their motions and compositions differ subtly from those of stars born within our galaxy, revealing their extragalactic origins. Each of these ancient mergers left behind faint imprints in the structure of the thick disk, like scars from cosmic collisions. In this sense, the thick disk serves as both a record and a witness of the Milky Way's turbulent past. Its stars preserve evidence of the violent events that helped build the galaxy we inhabit. Some may have been thrown into their current positions by gravitational interactions during early mergers, while others were formed in situ from gas that had been stirred and heated by these same collisions. The combination of these two origins, accreted stars from other galaxies and native stars formed within the Milky Way, explains the thick disk's complexity. It is not a simple or uniform layer, but a dynamic blend of populations that together tell the story of how the Milky Way grew. In addition to individual stars, the thick disk contains a few sparse open clusters, loose groups of stars that form together but are slowly drifting apart, as well as remnants of ancient globular clusters whose outer stars were stripped away by the Milky Way's gravity. Some of these remnants now exist as elongated stellar streams stretching across the sky. These features further emphasize how the thick disk connects the thin disk above and the halo beyond. It acts as a bridge between the regions of active star formation closer to the galactic plane and the ancient diffuse halo that extends into intergalactic space. The thick disk is dimmer and less dense than the thin disk, but it plays an essential role in defining the Milky Way's overall structure. Its existence proves that the galaxy is not a single flat layer of stars but a stratified system, with distinct populations separated by age, motion, and chemical composition. Without the thick disk, our understanding of the Milky Way would be incomplete. Its stars help astronomers define what below the plane truly means, revealing how the galaxy's vertical structure changes with distance from the center and from the midplane where our Sun resides. From a cosmic perspective, the thick disk reminds us that our solar system is just one part of a vast multi-layered galactic environment. Above us stretches the thin disk, filled with bright young stars, clusters, and nebulae glowing in ultraviolet light. Below us lies the thick disk, populated by ancient long-lived stars whose dim light tells the story of ages past. And beyond even that, surrounding everything extends the dark halo, a realm dominated by unseen matter, scattered star clusters, and faint stellar streams that mark the outermost reaches of our galaxy. These layers are not isolated from each other, but interconnected, bound together by gravity and by the shared history of the Milky Way's formation. The interplay between these layers reveals just how complex our galaxy truly is. The thick disk, once thought to be a simple structural feature, has proven to be a key to unlocking the Milky Way's evolutionary past. Its stars show that the galaxy did not form all at once, but grew gradually through mergers, collapses, and cycles of star birth and death. Each new generation of stars enriched the interstellar medium a little more, changing the chemistry of the gas from which future stars would form. Over billions of years, this process produced the varied structure we see today. Young metal-rich stars in the thin disk, older metal-poor stars in the thick disk, and ancient relics in the halo. In addition to its historical and structural importance, the thick disk holds great observational value. Because its stars are fainter and more spread out, they are often studied using infrared and spectroscopic techniques, which can penetrate dust and reveal subtle details of stellar composition. Astronomers measure the metallicity, temperature, and motion of these stars to estimate their ages and trace their origins. Surveys that map the thick disk in 3 dimensions have helped scientists reconstruct the Milky Way's vertical structure, showing how the density of stars decreases with distance from the plane and how their chemical composition changes from top to bottom. By examining stars below the solar system, researchers can distinguish between different stellar populations and identify which ones may have originated from ancient dwarf galaxies. This work has revealed that the Milky Way's growth was not smooth or uniform. It was shaped by multiple mergers and interactions over billions of years. Some stars now in the thick disk were once part of other galaxies, torn away and absorbed into our own. The chemical signatures of these stars serve as evidence of these past encounters helping scientists trace when and how they occurred. All of this information contributes to a more accurate picture of the Milky Way's mass and its distribution of both visible and invisible matter. The thick disk stars, because they move farther from the galactic plane than those in the thin disk, are particularly sensitive to the effects of dark matter. By analysing their velocities and accelerations, astronomers can infer the shape and density of the dark matter halo that surrounds the galaxy. This in turn helps refine models of how galaxies form and evolve across the universe. When viewed together, the thin and thick disks form a beautiful example of cosmic layering. The thin disk represents youth, activity, and ongoing creation, while the thick disk embodies age, memory, and endurance. The two are linked not only by gravity but also by a shared past. The thick disk may have given birth to the first generation of stars that later enriched the material forming the thin disk. In this way, the older layer beneath continues to influence the younger one above, even after billions of years. The thick disk is, therefore, far more than just a dim extension beneath the galactic plane. It is a vital chapter in the story of the Milky Way's life. Its stars act as historians, recording the ancient conditions of the universe and the early struggles of a galaxy finding its form. Their faint light carries the memory of cosmic collisions, of chaotic beginnings, and of the gradual settling that eventually gave rise to the calm, spiral beauty we see today. To study them is to look backward through time, to witness the formative moments of our home galaxy's creation. Every red dwarf, every white dwarf, every slowly orbiting star beneath the plane is a survivor of an era long gone. Together they compose an archive written not on paper, but in light and motion. By reading that archive, astronomers gain insight into the grand processes that govern galaxies everywhere, how they form, grow, and change across cosmic time. The thick disk stands as one of the Milky Way's oldest storytellers, its quiet stars whispering tales of the galaxy's birth and the endless dance of matter and gravity that continues to shape the universe today. The region below the galactic plane is not merely an empty extension of the Milky Way. It is a deep, ancient layer filled with meaning. It bridges the youthful brightness of the thin disk above with the mysterious vastness of the halo beyond, uniting the galaxy's past, present, and future. Understanding this layer is crucial to understanding the Milky Way itself, for it reveals the galaxy's vertical complexity and reminds us that even in the silent depths below the plane, the universe is alive with the echoes of creation. The Milky Way galaxy is not an empty void, but a region filled with enormous clouds of gas and fine dust, forming the fundamental material from which stars, planets, and eventually life itself originate. These areas of space, though they may appear dark and vacant when observed with the naked eye, actually contain vast and active structures that together make up what astronomers call the interstellar medium. The interstellar medium, often abbreviated as the ISM, is the collective name for all the gas, dust, and cosmic particles that fill the space between the stars in a galaxy. It is composed primarily of hydrogen and helium, with smaller quantities of heavier elements such as carbon, oxygen, nitrogen, and silicon. Despite being incredibly thin compared to the atmosphere on Earth, the interstellar medium extends through such a vast volume that it holds an immense amount of material, enough to sustain the formation of billions of stars over the lifetime of the galaxy. The density of the interstellar medium is remarkably low. In many regions, there are fewer than 1 atom per cubic centimetre, while the air we breathe on Earth contains roughly 10 billion molecules in the same volume. Yet, because the Milky Way stretches across more than 100,000 light-years, even this sparse material adds up to a colossal total mass. The interstellar medium acts as the connective tissue of the galaxy, linking stars, nebulae, and planetary systems in a continuous cycle of birth, death, and renewal. Matter expelled from dying stars through supernova explosions or stellar winds is recycled into this diffuse medium, where it mixes with existing gas and dust. Over time, gravitational forces, magnetic fields, and radiation from nearby stars cause portions of the interstellar medium to condense and form new generations of stars and planetary systems. Thus, the ISM plays a critical role in regulating the long-term evolution of the Milky Way. Above and below the galactic plane, the interstellar medium exists in different forms that correspond to variations in density, temperature, and composition. In the regions closest to the galactic plane, where the solar system is located, the medium is denser, and more active. These areas are part of the thin disk, a relatively flat layer extending a few hundred light-years above and below the galactic midplane. Here, gas clouds and dust concentrations are constantly interacting with stellar radiation and magnetic fields. This is where most of the galaxy's ongoing star formation takes place. Beyond this region, in the thicker disk lying farther above and below the plane, the density of matter decreases and star formation becomes less frequent. However, even in these more diffuse regions, gas and dust continue to play vital roles as reservoirs of raw material and as remnants of earlier phases in the Milky Way's history. The primary component of the interstellar gas is hydrogen, which is the most abundant element in the universe. Hydrogen in the ISM exists mainly in two forms: neutral atomic hydrogen, symbolized as Hi, and molecular hydrogen, written as H2. Neutral atomic hydrogen forms widespread, relatively diffuse clouds that can extend over thousands of light years. These clouds are particularly important because they emit radio waves at a wavelength of 21 centimeters, produced by a change in the spin orientation of the hydrogen atom's electron. This characteristic signal allows astronomers to map the large-scale structure of the Milky Way, even through regions obscured by dust. Using radio telescopes, scientists can trace the spiral arms of the galaxy and measure how gas moves under the influence of gravity, helping to determine the galaxy's overall mass and rotation curve. Molecular hydrogen, in contrast, is found in much denser and colder regions known as molecular clouds. These clouds represent the most fertile environments for star formation. Within them, temperatures can fall to only a few tens of degrees above absolute zero, allowing hydrogen atoms to bond together into H2 molecules. As the gas cools, it becomes more susceptible to gravitational collapse. When a section of a molecular cloud becomes dense enough, gravity overwhelms internal pressure and the cloud begins to contract. Over time, this collapse gives rise to one or more protostars surrounded by rotating disks of gas and dust. These disks eventually form planetary systems. The Orion Nebula, for instance, is a prominent example of a molecular cloud complex in which new stars are actively forming. Although this particular nebula lies within the thin disk of the galaxy above the solar system, similar processes occur in many regions across the Milky Way. In addition to hydrogen, helium constitutes the second most abundant element in the interstellar medium. Though helium is chemically inert and does not easily form compounds, it significantly contributes to the total mass and thermal behavior of the ISM. Trace elements, collectively referred to as metals in astronomical terminology, include carbon, nitrogen, oxygen, silicon, iron, and others. These heavier elements are produced within stars through nuclear fusion and are dispersed into space when stars shed their outer layers or explode as supernovae. The presence of such elements enriches the interstellar medium and allows for the formation of complex molecules, some of which contain the same types of chemical bonds found in organic matter on Earth. Astronomers have identified numerous organic compounds in interstellar clouds, including formaldehyde, methanol, and amino acid precursors. Their existence suggests that the building blocks of life are not unique to our planet, but may be widespread throughout the galaxy. The dust component of the interstellar medium consists of tiny solid particles, often less than 1 micrometer in size. These grains are composed mainly of silicates, carbon-based materials, and various types of ices that form under cold conditions. Dust plays several important roles in the evolution of the galaxy. First, it provides surfaces on which chemical reactions can occur, allowing simple atoms to combine into more complex molecules. Second, dust helps to cool dense regions of gas by emitting infrared radiation, a process that allows gravitational collapse to proceed more efficiently during star formation. Third, dust affects the way light travels through the galaxy. It absorbs and scatters starlight, leading to phenomena such as extinction and reddening. When starlight passes through dusty regions, shorter wavelengths, such as blue light, are scattered more strongly than longer wavelengths, making the stars appear redder than they truly are. This effect provides astronomers with clues about the amount and distribution of dust along the line of sight. Dust is also responsible for the dark nebulae seen in astronomical images, where thick concentrations of particles block background starlight. These features can be observed both above and below the galactic plane, and are particularly common along the spiral arms where dense molecular clouds reside. When illuminated by nearby stars, these clouds produce reflection nebulae, where light is scattered rather than absorbed, creating a characteristic blue tint. In some cases, ultraviolet radiation from hot young stars ionizes surrounding gas, producing emission nebulae that glow in distinct colours depending on their chemical composition. For example, hydrogen emits red light in the well-known H-alpha line, while oxygen can produce greenish or bluish hues. Such nebulae serve as indicators of recent star formation and help scientists understand the physical conditions of the interstellar medium. The interstellar medium is not uniform but structured into multiple phases, each characterized by different temperatures, densities, and ionization levels. The cold neutral medium, made of atomic hydrogen at temperatures of a few tens of kelvins, coexists with the warm neutral medium at several thousand kelvins. There are also warm ionized regions, primarily around young hot stars, where ultraviolet radiation has stripped electrons from atoms. In addition, the hot ionized medium, produced by supernova explosions, can reach millions of degrees. The interplay between these phases creates a constantly changing environment. Shock waves from supernova, stellar winds from massive stars, and the rotation of the galaxy all stir and mix the gas. Over time, material moves between phases, cooling, heating, condensing, or dispersing, as the galaxy evolves. Above the galactic plane, within the thin disk, interstellar clouds are relatively dense and often concentrated along the spiral arms. These are regions where the gravitational and dynamical effects of the galaxy's spiral pattern compress gas and dust, promoting star formation. Giant molecular clouds in these regions can extend for hundreds of light years and contain enough mass to produce tens of thousands of stars over periods of millions of years. Within these vast structures, localized star-forming regions develop where turbulence and self-gravity cause pockets of gas to collapse. Once massive stars form, their intense radiation, stellar winds, and eventual supernova explosions inject energy back into the surrounding medium. This energy both disrupts existing clouds and triggers new collapses elsewhere, creating a cycle of feedback that drives the long-term evolution of the galactic disk. Below the galactic plane, in the thicker disk, the situation differs. The gas and dust there are more diffuse and less active in forming new stars. These regions consist mainly of older material, remnants of earlier phases in the galaxy's development. The chemical composition of the thick disk often shows lower metallicity, that is, a smaller proportion of heavy elements, indicating that the gas has been less enriched by successive generations of stars. Over billions of years, material from the thick disk gradually mixes with the galactic halo, a much more extended and spherical component of the Milky Way. The halo contains ancient stars and globular clusters as well as hot ionized gas that may interact with material flowing in and out of the galactic disk. Through these processes, the thick disk acts as a transitional zone between the dense star-forming regions near the plane and the more tenuous outskirts of the galaxy. Interstellar gas and dust are also closely tied to the galaxy's magnetic field and the flux of cosmic rays, high-energy particles that travel through space at nearly the speed of light. The magnetic field influences the motion of charged particles within the interstellar medium and can guide the structure of gas clouds. At the same time, interactions between cosmic rays and interstellar matter affect the chemical and energetic balance of the ISM. The solar system itself moves in a slow oscillation above and below the galactic plane over a period of roughly 60 million years. As it passes through regions of differing density and magnetic intensity, the solar system experiences variations in the flux of cosmic rays. Denser clouds may shield it from some of this radiation, while more rarefied regions allow higher levels to penetrate. Such changes can subtly influence the radiation environment of the solar system and possibly affect the long-term conditions on Earth and other planets. Astronomers study the composition and distribution of interstellar gas and dust using a range of observational techniques across the electromagnetic spectrum. Radio telescopes detect the 21-centimeter line of atomic hydrogen, revealing the structure of the galactic disk and its spiral arms. Infrared observatories detect emission from dust grains heated by starlight, mapping regions that are otherwise hidden by optical extinction. Ultraviolet and X-ray instruments observe ionized gas and hot plasma, while optical telescopes capture the visible glow of emission nebulae. By combining data from all these wavelengths, scientists can build a three-dimensional model of the Milky Way structure. Such maps show that both above and below the solar system, the distribution of matter forms a layered system in which dense molecular clouds, diffuse atomic regions and hot ionized gas coexist in a complex balance maintained by gravity, pressure, and energy feedback from stars. The interstellar medium not only shapes the structure of the galaxy, but also influences the formation and evolution of planetary systems. Within molecular clouds, before stars form, a variety of complex organic molecules can assemble on the surfaces of dust grains. These molecules include simple sugars, alcohols, and amino acid precursors. When new stars form and planetary disks develop, this material becomes incorporated into comets, asteroids, and planetesimals. Over time, these small bodies can deliver organic compounds to young planets, potentially seeding the chemistry that leads to life. Studies of meteorites and comets in our own solar system show isotopic and molecular signatures that point to an interstellar origin. This evidence links the chemical processes in distant clouds to the ingredients that eventually made Earth habitable. The visual appearance of the Milky Way in the night sky is also a direct consequence of the interstellar medium. The bright milky band stretching across the sky represents our view through the densely populated disk of the galaxy, where starlight is combined with diffuse emission from gas and dust. When viewed in infrared wavelengths, this band reveals intricate patterns of dust lanes and glowing molecular clouds. Famous nebulae such as the Orion Nebula, the Eagle Nebula, and the Horsehead Nebula are visible manifestations of the same processes occurring above and below the solar system. In these regions, light from nearby stars illuminates the surrounding gas, creating striking colours and shapes that reflect the physical structure and chemical composition of the interstellar medium. Such nebulae are not merely decorative features of the galaxy, but active laboratories where the physics of star formation can be observed directly. The interstellar medium also serves as a record of the Milky Way's history. The relative abundances of elements within the gas and dust provide clues to how many generations of stars have lived and died in different parts of the galaxy. By measuring these abundances, astronomers can reconstruct the sequence of chemical enrichment that transformed the primordial hydrogen and helium left over from the Big Bang into the complex mixture of elements present today. Furthermore, the motion of gas clouds helps trace the gravitational forces shaping the galaxy. Deviations from expected orbital speeds indicate the presence of dark matter, an unseen component that exerts gravitational influence but does not emit or absorb light. Thus, observations of the interstellar medium contribute not only to our understanding of star formation, but also to the study of the fundamental structure and composition of the universe. In addition to internal processes, the interstellar medium interacts with material entering and leaving the galaxy. Streams of gas can flow inward from intergalactic space, replenishing the Milky Way's supply of raw material for star formation. At the same time, energetic events such as supernovae and galactic winds can expel gas into the surrounding halo, or even into intergalactic space. These inflows and outflows regulate the galaxy's long-term growth and maintain the balance of matter and energy. The boundaries between the galactic disk and halo are therefore not fixed but continuously shaped by these exchanges. Above and below the solar system, particularly in the outer reaches of the thick disk, such interactions play a significant role in defining the overall structure of the Milky Way. Without the interstellar medium, the Milky Way would be a static collection of aging stars slowly fading into darkness. Instead, the presence of gas and dust ensures a constant cycle of renewal. Stars are born, evolve, and eventually return material to the ISM, enriching it with heavier elements. This enriched material forms new stars and planets, continuing the process indefinitely. The solar system itself is a product of this cycle, formed about 4.5 billion years ago from the collapse of a molecular cloud that had been seeded with material from earlier generations of stars. The atoms that make up the Sun, Earth, and all living organisms were once part of the interstellar medium. Even today, the solar system remains embedded within this vast network of gas and dust, moving through it as the galaxy rotates. Within the wide layers of the Milky Way's thin and thick disks, and even stretching far into the less dense outskirts of the galaxy, lie immense and mysterious regions known as molecular clouds. These vast clouds of gas and dust are among the most fascinating and vital structures in the galaxy, for they serve as the cradles of stars, the very places where new suns are born. In a universe filled with light and energy, these regions stand out because they are some of the coldest and darkest places known. Yet within their silent, shadowy depths, the process that brings forth light itself quietly begins. Molecular clouds are very different from the more diffuse and widespread gas that fills much of the Milky Way. While the general interstellar medium consists of thinly spread atoms and ions, molecular clouds are far denser and far colder. Their temperatures typically fall between 10 and 30 degrees above absolute zero. In other words, from about 10 to 30 Kelvin, which equals roughly minus 263 to minus 243 degrees Celsius. These conditions are so cold that most atoms move sluggishly enough to bond together into molecules. The most common of these molecules is molecular hydrogen, known as H2, which forms when two hydrogen atoms join together. This simple molecule is the most important ingredient in the formation of stars. Without molecular hydrogen, the dense pockets of gas that give birth to stars would not be able to collapse and ignite. Along with molecular hydrogen, these clouds contain tiny grains of interstellar dust and traces of more complex molecules, such as carbon monoxide, ammonia, water vapor, and even organic compounds made of carbon, hydrogen, oxygen, and nitrogen, the same elements that form the basic chemistry of life. These compounds play essential roles in the chemical evolution of the galaxy. When stars form within these clouds, the materials around them are transformed by heat and radiation, leading to the creation of heavier elements and more intricate molecules. Some of these compounds may later become part of planets or comets, possibly providing the chemical seeds for the origin of life itself. Molecular clouds can be truly colossal in scale. Some are only a few light years wide, but others stretch across hundreds of light years, containing enough mass to form thousands of stars as massive as our Sun. One of the best-known examples is the Orion Molecular Cloud Complex, a spectacular region located above the galactic plane within the thin disk. This vast complex contains enough gas and dust to give birth to thousands of stars, and it is already home to many young, bright and hot stars that illuminate the famous Orion Nebula, one of the most photographed and studied regions in the entire night sky. The Orion Complex is a perfect example of how a cold, dark region of space can transform into a glowing nursery of newborn stars. Inside molecular clouds, matter is not evenly distributed. These clouds are not smooth spheres of gas, but are full of structure and complexity. They are threaded with long, wispy filaments, dense clumps, and compact cores, regions where gravity begins to take control. Within the densest of these cores, the force of gravity overwhelms the opposing pressure of heat and magnetic fields, causing the gas and dust to collapse inward. As the material falls toward the center, it heats up under compression, and over time, the temperature and pressure at the core rise high enough for nuclear fusion to ignite. When that happens, a new star is born. This process of star formation is gradual, taking millions of years to complete. At first, the collapsing region forms what is called a protostar, a young, still-forming star surrounded by a thick disk of gas and dust. As the protostar grows, it continues to draw in material from its surroundings, while some of that material forms a rotating disk that may later give rise to planets, asteroids, and comets. Eventually, the protostar becomes hot and dense enough for hydrogen fusion to begin in its core, marking the birth of a true star. The radiation from these young stars then begins to heat and push away the surrounding gas, sculpting the remaining cloud into striking shapes, bright glowing nebulae and dark silhouettes against the background of the Milky Way. When we look at photographs taken by telescopes such as the Hubble Space Telescope or the James Webb Space Telescope, many of the most beautiful and colourful nebulae we see, like the Eagle Nebula or the Carina Nebula, are actually regions of active star formation inside molecular clouds. The glowing colours in those images come from gas excited by the ultraviolet light of nearby young stars. In some areas, the clouds are so dense that even visible light cannot penetrate them, making them appear as dark patches blocking the stars behind them. These dark nebulae, though invisible in ordinary light, are rich in potential, hiding countless stars that have not yet been born. Below the galactic plane, molecular clouds also exist, though they are fewer and often less active than those above it. The thick disk of the Milky Way contains older stars and less gas overall, but the clouds found there still play an important role in the galaxy's evolution. Star formation in these lower regions happens more slowly and less frequently, but that does not make it less meaningful. These clouds preserve the remnants of earlier generations of stars. material enriched with heavier elements produced by long-dead suns. Some of this gas may have drifted outward from the thin disk, while other portions might have come from smaller satellite galaxies that once interacted with the Milky Way. In this way, the molecular clouds of the thick disk hold the chemical memories of ancient cosmic events, linking the past and present of our galaxy. By studying molecular clouds in both the thin and thick disks, astronomers can trace how the Milky Way has changed over time. The differences in density, temperature, metallicity, and turbulence between clouds located above and below the solar system help scientists understand why certain regions produce clusters of massive, short-lived stars, while others favour smaller, longer-lived ones. These variations can also influence the formation of planets. A cloud rich in heavy elements is more likely to form rocky worlds similar to Earth, while a more pristine, metal-poor cloud may form mostly gas giants or barren systems. Molecular clouds are not static or peaceful. They are dynamic, restless environments shaped by the constant tug of gravity, the influence of magnetic fields, and the violence of nearby stars. Magnetic fields thread through the clouds like invisible webs, guiding the motion of charged particles and offering resistance to gravity. These fields help slow down or regulate the rate of star formation, preventing the entire cloud from collapsing at once. At the same time, shock waves from supernova explosions, the deaths of massive stars, can travel through space and compress portions of these clouds, triggering new bursts of star formation. This process, called triggered star formation, creates a chain reaction in which one generation of stars gives rise to the next. The energetic winds and radiation from young, hot stars can also sculpt nearby gas into elegant arcs and pillars, pushing some regions together and dispersing others. Over millions of years, this constant interplay of forces, gravity pulling inward, magnetic fields resisting, radiation pushing outward, and turbulence stirring the gas, shapes molecular clouds into spectacular forms. Some take on towering pillar-like shapes, others stretch into long filaments or bubble-like cavities. These patterns are not just visually striking, but also scientifically revealing, for they trace the hidden processes governing the birth of stars. When ultraviolet radiation from newborn stars strikes the surrounding hydrogen gas, it causes the gas to glow, creating what astronomers call emission nebulae. In contrast, areas so dense that light cannot pass through appear as dark nebulae, casting eerie shadows across the glowing background. Both kinds of structures tell part of the story of how the Milky Way continually renews itself. Molecular clouds are essential to understanding not only how stars are born, but also how galaxies evolve. They are key players in the cosmic recycling system that keeps the Milky Way alive and active. When old stars die, either through gentle outflows or violent supernova, they return their material to space, gas enriched with heavy elements like carbon, oxygen, silicon, and iron. This material mixes with the existing interstellar medium, eventually becoming part of new molecular clouds. Over time, those clouds collapse to form new stars and planets, which will eventually enrich the galaxy once again when they die. This cycle of birth, death, and rebirth of stars has been occurring for billions of years, maintaining the galaxy's vitality. Above and below the solar system, molecular clouds silently perform this role, shaping the balance of matter and energy in the galactic environment. They act as cosmic nurseries, quietly preparing the next generations of stars that will shine across the Milky Way for millions or even billions of years. The story of our own solar system likely began in one such cloud about 4.5 billion years ago. Within that ancient cloud, gravity gathered gas and dust into a dense core, which collapsed to form the young sun, surrounded by a disk of material that later became the planets, moons, and comets we know today. In this sense, molecular clouds are not merely distant astronomical phenomena, they are directly connected to our own existence. Every atom in our bodies, every grain of sand on Earth, and every molecule of water once passed through the cycle of stellar birth and death that begins in these clouds. Molecular clouds also serve as natural laboratories for studying complex chemistry in space. Because they are cold and shielded from harsh ultraviolet radiation, they provide ideal conditions for molecules to form and survive. Observations made in radio, infrared, and submillimeter wavelengths reveal that these clouds contain a surprising variety of molecules. More than 200 different kinds have been identified so far. Among them are simple compounds like water and carbon monoxide. but also more complex organic molecules such as formaldehyde, methanol, ethanol, and even simple sugars. Some of these compounds could eventually become part of forming planets, comets, or asteroids, carrying the building blocks of life across the galaxy. Astronomers use specialized telescopes on Earth and in space to study these clouds. Because visible light cannot penetrate the dense dust, scientists rely on other parts of the electromagnetic spectrum such as radio and infrared waves, which can pass through the obscuring material. Instruments like the Atacama Large Millimeter Array in Chile and the Herschel Space Observatory have provided detailed maps of the structure and composition of molecular clouds. These observations show that clouds often contain many layers and regions with different physical properties, some cold and quiescent, others warm and turbulent. This complexity helps explain why star formation is not uniform, but occurs in bursts and clusters. The dynamics of molecular clouds are deeply linked to the overall structure of the Milky Way. The galaxy's spiral arms, which sweep gracefully through space, are partly defined by the presence of these clouds. As the Milky Way rotates, regions of higher density in the spiral arms compress gas and dust, encouraging the formation of new clouds. These clouds, in turn, produce new generations of stars that light up the arms, maintaining their spiral pattern. Between the arms, where the density is lower, fewer molecular clouds exist and star formation is much slower. Thus, molecular clouds help shape the visible structure of the entire galaxy. As the solar system orbits the center of the Milky Way, it moves not only around the galactic plane but also oscillates slightly above and below it in a slow, wave-like motion that takes tens of millions of years to complete. During this motion, the solar system passes through regions of varying density, sometimes through areas rich in molecular clouds, and sometimes through more empty regions of interstellar space. Although these clouds usually lie far enough away to have no direct effect on the planets of our solar system, they do influence the overall galactic environment. The density of gas and dust in the neighborhood of the Sun can affect cosmic rays, interstellar radiation, and even the outermost reaches of the heliosphere, the vast bubble of charged particles created by the solar wind. The vertical distribution of molecular clouds in the Milky Way offers further insight into the galaxy's three-dimensional structure. Denser clouds tend to concentrate closer to the galactic plane, where most star formation occurs, while sparser and more fragmented clouds extend into the regions above and below, gradually blending into the galactic halo. This layering reflects the balance of gravity, pressure, and turbulence within the galaxy, much like the layers of an atmosphere on a planet. By studying this vertical structure, astronomers can better understand how matter circulates between different regions of the Milky Way, and how the galaxy maintains its delicate equilibrium over billions of years. Every molecular cloud represents a link in the great chain of cosmic evolution. They hold within them the ashes of past stars and the potential for future ones. When a massive star forms and lives out its short, brilliant life, it eventually explodes in a supernova, scattering heavy elements far into space. Those elements enrich nearby clouds, ensuring that the next generation of stars and planets will contain more complex materials. This gradual enrichment process explains why younger stars, including our Sun, contain heavier elements that older stars lack. Over time, this cycle has transformed the Milky Way from a galaxy of mostly hydrogen and helium into one filled with a wide variety of chemical elements, the ingredients of planets, oceans, and life itself. Even though they are dark and cold, molecular clouds are far from lifeless. They are dynamic systems filled with motion, turbulence, and change. The balance between collapse and expansion within them determines when and where stars will form. Some clouds remain relatively quiet for tens of millions of years, while others undergo rapid transformation after being struck by shock waves or gravitational disturbances. These variations create the diversity of stellar nurseries we observe today, from calm, diffuse clouds like those in Taurus to massive, turbulent complexes like Orion and Carina. When viewed through radio telescopes, molecular clouds appear as intricate webs of filaments, knots, and voids. Computer simulations suggest that these patterns arise naturally from the chaotic interplay of gravity, turbulence, and magnetic forces. Despite their apparent disorder, the formation of stars within these clouds follows certain statistical patterns, leading to consistent distributions of star masses across the galaxy. This regularity shows that, even amid the chaos of interstellar space, natural laws operate with remarkable precision and predictability. The study of molecular clouds therefore reaches far beyond the clouds themselves. It touches on questions about how galaxies form and evolve, how planets arise, and even how life may begin. By tracing the path of matter from diffuse interstellar gas to dense molecular clouds, to stars, to planets, and finally to living organisms, scientists can piece together the grand narrative of cosmic evolution, a story that connects the smallest molecules to the largest galactic structures. Molecular clouds above and below the solar system are not just silent accumulations of gas. They are active participants in this ongoing drama. Their cold darkness conceals the most creative process in nature, the birth of stars. They provide the raw material from which everything visible in the night sky is ultimately made. They regulate the rhythm of the Milky Way's life cycle and preserve the chemical memory of generations of stars long vanished. They show us that our galaxy is not a static collection of stars but a living, changing system, constantly renewing itself through cycles of destruction and creation. Beyond the relatively thin disk that holds most of the young and middle-aged stars, there exist some of the most ancient and mysterious stellar systems in the galaxy. These are known as globular clusters. Each globular cluster is a massive, tightly bound, and nearly spherical group of stars that can contain anywhere from a few 100,000 to several million individual suns. They are held together by their mutual gravity, forming dense, compact collections that have survived for billions of years, long before the Earth or even the Sun came into existence. Unlike the more familiar stars scattered throughout the thin and thick disks of the Milky Way, the stars inside globular clusters are packed with extraordinary density, especially near their cores. In the region surrounding our Sun, stars are separated by an average distance of several light years. But in the crowded centers of globular clusters, the separation between stars can be only a small fraction of a light year, meaning that thousands of stars can fit into the space that in our local region might contain only one. This immense concentration of mass gives globular clusters their intense gravitational stability and their bright, glowing appearance. Because of their roughly spherical shape, globular clusters do not lie within the flat plane of the Milky Way's disk. Instead, they orbit in the galactic halo, a vast, faintly populated region that extends tens of thousands of light years above and below the galactic plane. When viewed from a great distance, the entire system of these clusters forms a kind of three-dimensional scaffolding around the Milky Way, surrounding the flat disk like a sphere of shining beads. This grand structure has endured for more than 10 billion years, longer than almost any other feature of the galaxy. From the perspective of observers on Earth, each globular cluster appears as a small, jewel-like orb of light, a glowing lantern suspended in the deep darkness of space. The light that reaches us from such a cluster is not the light of a single star, but the combined glow of hundreds of thousands of ancient suns, their radiance blending together to form a brilliant, compact sphere. These clusters are not only visually impressive but scientifically invaluable, for they preserve within their ancient stars a direct record of the conditions that prevailed in the early universe. Most of the stars that make up the Milky Way's globular clusters formed soon after the galaxy itself began to assemble. This makes them among the oldest surviving stellar populations known to science. The stars within them are generally small, long-lived, and composed of relatively simple chemical elements, mainly hydrogen and helium, with only trace amounts of heavier materials such as carbon, oxygen, or iron. Astronomers refer to such stars as metal-poor because the term metals in astrophysics refers to all elements heavier than helium. Their lack of heavy elements indicates that these stars formed before the first generations of supernovae had time to seed the galaxy with the byproducts of nuclear fusion. This chemical simplicity allows astronomers to use globular clusters as natural laboratories for studying the universe's earliest history. The low metallicity of their stars shows that the clusters were born from primordial gas clouds that had not yet been enriched by stellar explosions. By analysing the light from these stars, researchers can infer what the interstellar medium of the young Milky Way was like, and how star formation operated when the universe was still in its youth. In this sense, globular clusters are like cosmic time capsules, frozen records of a period when the first stable structures were emerging from the chaos that followed the Big Bang. Even though the stars in these clusters are extremely old, most of them continue to shine. Because they are generally of low mass, they consume their nuclear fuel at a slow rate, giving them lifetimes that stretch into many billions of years. Many of them have evolved into red giants, large and luminous stars in the later stages of their lives. Others have reached the horizontal branch phase, where they burn helium in their cores after exhausting the hydrogen that once powered them. Some of the oldest stars have already ended their active nuclear burning and have become white dwarfs, faint, dense remnants that gradually cool over time. Despite these changes, the clusters themselves remain gravitationally bound, preserving their dense structure for astonishing lengths of time. Globular clusters are not distributed evenly throughout the Milky Way. They do not belong to the thin disk, which contains most of the young stars and star-forming regions, nor to the thicker disk, which is populated by older but still rotating stars. Instead, globular clusters belong to the galactic halo, a vast spherical region that extends tens of thousands of light-years beyond the galactic plane. Some of these clusters are relatively close to the solar system, lying only a few thousand light-years away, while others orbit at distances of more than 100,000 light-years, tracing the faint outer boundaries of the galaxy's gravitational reach. The orbits of globular clusters are typically elongated rather than circular, and they are often inclined at steep angles relative to the galactic plane. This explains why, when astronomers map their locations, the clusters appear as scattered points of light above and below the disk, isolated stellar islands drifting through the halo. Their distribution forms a kind of invisible skeleton that outlines the Milky Way's gravitational structure. By carefully studying their motions, astronomers can estimate the total mass of the galaxy, including the mysterious dark matter that makes up most of its gravitational pull but emits no light of its own. The stars that populate globular clusters belong primarily to what astronomers call population 2, a classification that refers to their low metallicity and great age. These stars formed from gas clouds composed almost entirely of hydrogen and helium, the simplest and most abundant elements in the universe. In contrast, younger stars in the thin disk of the Milky Way, including the Sun, belong to population 1, meaning that they contain much higher proportions of heavier elements. The difference in chemical composition affects many aspects of a star's behavior, including its color, temperature, and rate of evolution. Population 2 stars tend to be slightly bluer and less luminous than metal-rich stars of the same mass, and they evolve more slowly, allowing them to persist for enormous spans of cosmic time. Because globular clusters are so densely packed, they provide an environment very different from that of ordinary stellar neighborhoods. The gravitational interactions among the stars are intense, and close encounters occur frequently. Over time, these interactions can lead to a wide variety of dynamic processes. Some stars may exchange energy, causing their orbits within the cluster to shift. In rare cases, two stars may collide or merge, forming a single, more massive star. Binary star systems, pairs of stars orbiting each other, are especially common in globular clusters, and interactions between binaries and single stars can result in complex exchanges of energy and momentum. These internal dynamics can gradually alter the structure of a cluster over billions of years, a process known as dynamical evolution. The densest regions tend to lose energy as stars exchange momentum, leading to a phenomenon called core collapse, in which the central region becomes even denser. Meanwhile, some stars gain enough energy from interactions to escape the cluster entirely, drifting into the halo as isolated wanderers. Despite this constant internal motion, the cluster as a whole remains gravitationally bound and remarkably stable, with its overall structure persisting through cosmic time. The crowded environments of globular clusters also give rise to unusual and exotic types of stars that are rarely found elsewhere. One example is the blue straggler, a star that appears unexpectedly young and bright compared to the surrounding population. Blue stragglers are thought to form when two stars merge, or when one star in a binary system transfers mass to its companion, effectively rejuvenating it. Another example is the millisecond pulsar, a rapidly rotating neutron star with an intense magnetic field that emits regular pulses of radiation. Such objects serve as extraordinarily precise cosmic clocks, and when found in globular clusters, they allow astronomers to probe the gravitational and magnetic conditions within these dense systems. Variable stars whose brightness changes over time are also common and have long been used to measure distances to the clusters and to calibrate the cosmic distance scale. In this way, globular clusters are not merely static relics, but living laboratories where stellar evolution, dynamics, and exotic physics can all be observed together. They illustrate how gravity shapes stellar systems on both small and large scales, and how interactions between stars can influence their individual and collective fates. Globular clusters also offer critical evidence about the history of the Milky Way itself. Not all of them were born within our galaxy. Astronomers have discovered that some clusters were likely captured from smaller satellite galaxies that merged with or were absorbed by the Milky Way billions of years ago. These captured clusters can be identified by their chemical compositions and orbital characteristics, which differ from those of clusters that formed natively within the Milky Way. In this sense, globular clusters act as fossils of galactic evolution, preserving within their stars the signatures of ancient collisions and mergers. By studying their positions and motions, scientists can reconstruct the hierarchical process by which the Milky Way grew to its current size, through the gradual accretion of smaller systems over cosmic time. Clusters that now orbit far above and below the galactic plane may once have belonged to dwarf galaxies that were drawn in by the Milky Way's gravity. Their stars and clusters were stripped away and incorporated into the halo, leaving behind faint tidal streams that still trace the paths of those long-vanished systems. Because globular clusters inhabit the relatively quiet environment of the halo, far from the disruptive gravitational influences of the galactic disk, they have survived with their structure largely intact for more than 10 billion years. This makes them unique witnesses to the earliest epochs of the galaxy's formation. Their stability and longevity mean that they can still tell astronomers what the Milky Way was like when it was young, before the spiral arms took shape and before most of its stars were born. From an observational perspective, globular clusters are among the most striking and easily identifiable objects in the night sky. Even small telescopes can reveal some of the nearer clusters as dense, round patches of light, while larger instruments or space-based observatories can resolve them into thousands of individual stars. When imaged in detail, a typical cluster shows a brilliant core surrounded by a gradually thinning halo of stars, fading smoothly into the darkness of space. For the nearest clusters, such as Omega Centauri or Messier 13, individual stars can be clearly distinguished, and their properties measured with great precision. More distant clusters, on the other hand, appear as smooth, glowing orbs whose light represents the combined radiance of innumerable stars. Astronomers have catalogued and studied hundreds of globular clusters, both within the Milky Way and in nearby galaxies, determining their distances, ages, and metallicities. These measurements are essential for testing theories of stellar evolution and for calibrating the overall timeline of galactic history. Above and below the solar system, globular clusters form a vast vertical network that outlines the shape of the galactic halo. Their distribution contrasts sharply with the relatively flat, continuous layer of stars in the thin and thick disks. The halo's sparse population means that each cluster stands out clearly against the dark background of interstellar space, serving as a luminous marker of the Milky Way's extended structure. Beyond their role within our own galaxy, globular clusters have profound importance for cosmology as a whole. Because they contain some of the oldest known stars, measuring their ages provides a lower limit for the age of the Milky Way, and even for the universe itself. The oldest clusters have been dated to more than 12 billion years, indicating that they formed not long after the universe's first billion years had passed. In this way, globular clusters serve as timekeepers of cosmic history. Their internal motions also reveal information about the invisible matter that dominates galaxies. By studying the velocities of stars within a cluster, astronomers can estimate its total mass and determine how tightly it is bound by gravity. When the motions of many clusters throughout the halo are combined, the results can be used to map the Milky Way's gravitational potential and to infer the distribution of dark matter. Thus, the study of these ancient star systems contributes directly to our understanding of one of the universe's deepest mysteries. The continued survival of globular clusters over billions of years is a testament to the delicate balance between gravitational attraction, stellar evolution, and galactic dynamics. While individual stars within the Milky Way are constantly forming and dying, and while spiral arms shift and gas clouds drift through the disk, the clusters remain steadfast, compact, coherent, and enduring. They represent the oldest surviving witnesses of the galaxy's formation and evolution, preserving a memory of a time when the Milky Way was still gathering its mass from the surrounding cosmic environment. Each cluster above and below the solar system shines as a remnant of that distant past, a cosmic lantern illuminating the long story of stellar birth, life, and death. The ancient stars within these clusters contrast sharply with the young, bright populations that fill the thin disk, where new stars continue to form within molecular clouds. They also differ from the older, more diffuse stars of the thick disk that surround the galactic plane. Together, these different components, the thin disk, the thick disk, and the halo of globular clusters, illustrate the vertical complexity of the Milky Way, revealing it not as a flat, uniform structure, but as a layered and dynamic system with deep historical roots. By examining globular clusters, astronomers gain insight into the Milky Way's origin, its long-term evolution, and the universal processes that govern the behavior of stars and galaxies. These ancient, gravitationally bound spheres provide evidence of the earlier star formation, of the build-up of chemical elements through time, and of the interactions that have shaped the galaxy's mass and structure. Surrounding all the visible parts of the Milky Way, the thin disk, the thick disk, and the many ancient globular clusters, is an enormous mysterious structure known as the galactic halo. This halo is not a flat disk like the rest of the galaxy, but a vast, roughly spherical region that stretches far above and below the galactic plane. It acts as a kind of invisible shell that surrounds the entire Milky Way, extending outward across an unimaginable distance. While the disks of the galaxy are crowded with stars, gas, and dust, the halo is faint and sparsely populated, made up mostly of ancient stars, hot gas, globular clusters, and a huge, unseen component known as dark matter. Together, these elements form one of the most fascinating and essential parts of our galaxy, a region that links the Milky Way's bright, visible center to the dark reaches of intergalactic space. Unlike the orderly, flat structure of the galactic disks, where stars orbit the center in smooth circular paths, the halo is chaotic and diffuse. The stars within it are scattered across vast distances, with little pattern or uniformity. The halo stretches for tens of thousands of light-years from the galactic plane, and some estimates suggest that its outer boundaries may extend to nearly 300,000 light-years from the center of the Milky Way. This immense size makes the halo not only one of the largest structures within our galaxy, but also its outermost limit, the region where the gravitational influence of the Milky Way fades into the emptiness of intergalactic space. In many ways, the halo forms the bridge between our galaxy and the wider universe, defining the outer edge of the Milky Way's gravitational reach. The stars that populate the galactic halo are among the oldest in existence. They belong to what astronomers call Population II stars, ancient stellar generations that formed early in the Milky Way's history, long before the thin disk and spiral arms came into being. These stars have very low metallicity, meaning they contain only small amounts of elements heavier than hydrogen and helium. This lack of heavy elements tells scientists that these stars were born at a time when the universe was still young and had not yet been enriched by countless cycles of star formation and supernova explosions. Compared to the dense and active stellar neighborhoods in the galactic disk, halo stars are extremely sparse and widely separated. Their orbits are also very different. Instead of following the smooth circular paths of stars in the thin disk, halo stars travel on highly elongated and randomly oriented orbits, giving the halo its roughly spherical shape and contributing to its unique, almost ghostly character. Many of these halo stars did not form within the Milky Way itself. Instead, they are remnants of smaller galaxies that once orbited our own before being torn apart by its powerful gravitational forces. Over billions of years, the Milky Way has grown by absorbing these smaller companions, pulling in their stars, gas, and dark matter to build up its halo. The traces of these ancient mergers can still be seen today in the form of faint streams of stars, long arcing trails left behind by dwarf galaxies that were captured and disintegrated. By studying the chemical composition and motion of halo stars, astronomers can reconstruct the Milky Way's long and complex history, piecing together the story of how our galaxy assembled itself from smaller fragments scattered throughout the early universe. Each halo star, in this sense, is a tiny time capsule carrying clues about events that occurred billions of years ago, long before the Sun or Earth came into existence. Embedded within this vast and ancient halo are the Milky Way's globular clusters, dense, spherical gatherings of hundreds of thousands or even millions of stars bound tightly together by gravity. These clusters hover high above and far below the galactic plane, glowing like tiny jewels suspended in the darkness. Because they are so strongly bound, they can survive the constant gravitational disturbances caused by nearby stars or by the pull of the galactic centre. Each globular cluster serves as a small, stable island of light within the halo's sparse environment. The stars within them are some of the oldest known in the galaxy, and studying them helps astronomers understand the earliest periods of stellar evolution. These clusters not only enrich the halo visually, but also serve as vital markers that reveal the structure and motion of the Milky Way on its grandest scales. In addition to these clusters, the galactic halo is filled with faint stellar streams, the remains of smaller galaxies and clusters that were gradually torn apart by the Milky Way's gravity. These streams trace graceful paths across the sky, forming delicate arcs that wrap around the galaxy. Observing them gives astronomers a direct window into the Milky Way's ongoing growth and transformation. They show that the halo is not a static or unchanging region, but one that continues to evolve. Even now, small galaxies are being drawn into the Milky Way, their stars stripped away and absorbed into the halo's vast stellar population. These events provide a living record of galactic evolution in action. Moreover, the way these streams move through space offers crucial information about the distribution of dark matter, since their paths are shaped by the invisible gravitational field that dark matter creates. Thus, by studying the orbits of these streams, scientists can map the unseen mass that fills the halo and dominates the galaxy's structure. The halo, however, is not made of stars alone. It also contains large amounts of hot, ionized gas that form what is known as the circumgalactic medium. This gas is extremely thin, so tenuous that it would make even the emptiest vacuum on Earth seem dense by comparison, but it extends across enormous distances. Despite its low density, it plays a vital role in the life of the galaxy. The temperatures within this medium reach into the millions of degrees Kelvin, making it one of the hottest components of the Milky Way. This searing gas acts as a reservoir of material that can both feed star formation and regulate it. When massive stars reach the ends of their lives and explode as supernovae, they eject heavy elements and energetic winds into space. Much of this material escapes from the galactic disk and travels into the halo, where it enriches the surrounding gas with newly formed elements. Over time, some of this gas cools and falls back toward the disk in a process known as the galactic fountain. In this way, matter continually circulates between the disk and the halo, ensuring that the two regions remain connected in a dynamic cycle of enrichment and renewal. Studying this hot halo gas is no simple task. Because it emits most of its energy in the form of high-energy radiation, it can only be observed through X-ray and ultraviolet telescopes. These instruments reveal faint glows and spectral lines that trace the structure and movement of the gas across vast stretches of space. Through such observations, astronomers can map the size, temperature, and density of the Milky Way's circumgalactic medium, uncovering the processes that drive the evolution of the entire galaxy. Far from being an inert or passive shell, the halo is an active and vital component of the Milky Way's ecosystem, a cosmic recycling center that connects the birth and death of stars, regulates the flow of matter, and mediates the exchange of energy between the galaxy and intergalactic space. Yet perhaps the most mysterious and significant part of the halo is something that cannot be seen at all: dark matter. This elusive substance, which neither emits nor absorbs light, is believed to make up most of the halo's total mass. It forms a roughly spherical cloud that surrounds and envelops all the visible components of the Milky Way: the disks, the stars, the clusters, and even the interstellar gas. The gravitational influence of this dark matter is essential to the galaxy's stability. Observations show that stars in the outer regions of the Milky Way orbit much faster than they should if only visible matter were present. The extra gravitational pull needed to explain these high speeds can only come from the invisible mass of the dark matter halo. Without it, the galaxy's stars and gas would not remain gravitationally bound. The Milky Way would slowly disperse into space. Thus, even though dark matter cannot be seen directly, it is the hidden framework that holds the galaxy together, shaping its form and governing its motion. Above and below the solar system, the halo stretches outward in every direction, defining the environment through which our galaxy moves. The stellar density here is extremely low. The nearest halo stars may lie several thousand light-years away, leaving vast regions of apparent emptiness. But this emptiness is deceptive. It is filled with invisible forces and delicate structures, Streams of stars, globular clusters, clouds of hot gas, and immense quantities of dark matter, all interacting with one another in subtle ways. These interactions affect the motion of stars within the disks, the dynamics of satellite galaxies, and even the long-term evolution of the Milky Way itself. Because the halo is so faint, it is difficult to observe directly, but its presence is felt everywhere, influencing the structure and behavior of the galaxy as a whole. The transition from the dense thin disk to the more diffuse thick disk and finally into the nearly empty halo reveals the layered complexity of our galaxy. From the crowded star fields of the inner regions to the vast expanses of the outer halo, the Milky Way forms a continuous structure that extends far beyond the boundaries visible to the naked eye. Our solar system, located within the thin disk, is just one small part of this intricate multi-dimensional system. Though we live in a relatively flat and bright region of the galaxy, we are surrounded on all sides by the invisible expanse of the halo, which stretches far above and below us into the cosmic darkness. One of the most remarkable aspects of the halo is the presence of small companion galaxies, satellite systems that orbit within its immense volume. Among the most notable of these are the Sagittarius dwarf galaxy and the Large and Small Magellanic Clouds. These dwarf galaxies travel along complex orbits around the Milky Way, sometimes passing close enough to interact with the outer disk. When this happens, gravitational forces distort both the satellites and the Milky Way itself, drawing out long tidal tails and streams of stars. Over time, these dwarf galaxies lose material to the halo, feeding it with new stars and gas that become part of the Milky Way's extended structure. These ongoing interactions show that the halo is not simply a relic of the distant past. It is a living, evolving environment still being shaped by cosmic forces today. The halo also affects the solar system in subtle but important ways. As the Sun and its planets travel around the centre of the Milky Way, they oscillate up and down through the galactic plane, sometimes moving closer to the halo and sometimes farther away. Although the halo's gas and stars are too sparse to have a direct impact on our everyday environment, its gravitational influence extends across the galaxy. It helps stabilise the orbits of satellite galaxies, affects the paths of distant globular clusters, and even influences the distribution of comets in the Oort cloud at the outermost reaches of the solar system. The enormous mass of the halo ensures that all the visible parts of the Milky Way remain gravitationally bound, preventing stars, including our Sun, from drifting away into intergalactic space. In essence, the galactic halo serves as the great cosmic envelope that contains and protects the Milky Way. It stretches far beyond the visible disks, encompassing the thin and thick layers, the clusters, the satellites, and the streams that orbit within it. It is a vast, nearly spherical domain composed of ancient stars, glowing clusters, searing hot gas, invisible dark matter, and faint traces of countless past collisions and mergers. Every element within it contributes to the galaxy's ongoing story. The stars preserve the memory of the Milky Way's earliest days. The gas circulates between the halo and the disk, fueling the creation of new generations of stars. The dark matter forms the underlying framework that keeps everything bound together. Together, they reveal a picture of a galaxy that is not static but alive, an ever-changing system that grows, evolves, and interacts with the universe around it. Studying the galactic halo gives astronomers a rare three-dimensional perspective on the Milky Way. It allows them to see how the visible components of the galaxy, its bright disks, glowing clusters, and familiar stars, fit within a much larger and mostly invisible structure. The halo extends far beyond what can be seen through ordinary telescopes, reminding us that the Milky Way we perceive with our eyes is only a fraction of the whole. What appears to us as a flat band of light stretching across the night sky is in truth part of a vast spherical system that surrounds us completely. The halo stands as a living record of the Milky Way's past and a guide to its future. Its ancient stars tell the story of the galaxy's formation. Its stellar streams trace the paths of long-vanished companions. Its hot gas regulates the ongoing cycle of star birth and death, and its dark matter binds it all together. It represents both the memory and the backbone of the Milky Way, the invisible architecture upon which everything else depends. While we may dwell within the bright and crowded disk, it is the halo that defines the true scale and grandeur of our galactic home. Every movement of the Milky Way, its rotation, its gravitational pull, its evolution across billions of years, is shaped by the unseen presence of this enormous sphere. The halo is not just an outer layer, but an integral part of the galaxy's identity. It links the oldest stars to the newest, the visible to the invisible, and the local to the cosmic. Through it, we come to understand that the Milky Way is not merely a flat spiral of stars, but a vast, multi-layered and deeply interconnected structure reaching out into the depths of intergalactic space. And so, even as our solar system travels quietly within the thin disk, we remain part of this far-reaching system, connected to the ancient stars above and below, bound by the gravity of unseen matter, and surrounded by the faint glow of the galaxy's invisible halo. It is through the study of this immense, mysterious region that we gain the most complete understanding of what the Milky Way truly is, not just a collection of stars and planets, but a living cosmic organism bound together across space and time by the delicate and powerful forces of the galactic halo. Surrounding the shining stars, glowing gas, and swirling dust of the Milky Way is an enormous and invisible realm that few can truly imagine. This unseen domain is known as the dark matter halo, a vast and mysterious structure that stretches far beyond everything we can see in the night sky. It lies both above and below the plane of our galaxy, surrounding not only the solar system, but the entire Milky Way itself, like a gigantic invisible sphere. Even though it cannot be seen, it is believed to be one of the most important parts of our galaxy, silently shaping its destiny and keeping it from flying apart. Unlike the stars and nebulae that fill the Milky Way's bright spiral arms, dark matter does not shine, does not absorb light, and does not reflect it. It is truly invisible. No telescope, no matter how powerful, can detect it directly. Yet astronomers are certain that it exists, because they can see what it does. It leaves behind unmistakable signs through its gravitational pull, influencing how stars, clusters, and even whole galaxies move through space. It is as if the universe has a hidden skeleton, invisible to our eyes but essential to its structure. This unseen framework, made of dark matter, holds the Milky Way together and gives it its shape. The evidence for this mysterious halo comes from how stars move. When astronomers began to study the speed of stars in different parts of galaxies during the 1970s, they noticed something strange. According to the laws of physics first described by Isaac Newton centuries earlier, stars closer to the center of a galaxy should move faster, while those farther out should move more slowly. But when scientists measured the actual speeds of stars in the outer regions, they found that these stars were moving just as fast as, or even faster than, those near the center. Something was providing extra gravity to keep them from drifting away into space. That something, although unseen, had to exist, and it was far more massive than all the visible stars combined. This discovery marked the birth of the modern concept of dark matter. In the Milky Way, dark matter is thought to form a vast, roughly spherical halo that extends far beyond the luminous parts of the galaxy. While the bright disk of the Milky Way spans about 100,000 light-years across, the dark matter halo could stretch several 100,000 light-years from the galactic center, perhaps even farther. This means that our entire solar system, along with all the stars, star clusters, and interstellar clouds we can see, are floating within this gigantic invisible bubble of mass. The dark matter halo is so immense that it outweighs all the ordinary matter in the Milky Way. In fact, scientists estimate that the visible material, the stars, planets, gas, and dust, makes up only a small fraction of the total mass of our galaxy. The rest, the majority, is dark matter. This enormous halo acts like a powerful gravitational anchor. It prevents the galaxy's outer stars from flying off into intergalactic space and holds together the delicate spiral structure of the Milky Way. Without it, the galaxy as we know it would not exist. The thin and thick disks filled with stars of different ages would likely be torn apart by gravitational forces, and the entire system would slowly unravel. Instead, thanks to the dark matter halo, the Milky Way remains stable, its stars following graceful orbits around the galactic center. The dark matter halo envelops every part of the Milky Way. It surrounds the thin disk, where young stars and nebulae shine brightly. It encompasses the thicker disk, which contains older and dimmer stars, and it even stretches around the globular clusters that orbit the galaxy's outskirts. Beyond these, it merges with the more diffuse galactic halo that contains ancient stars and stray interstellar material. Altogether, the dark matter halo forms an immense gravitational cocoon that stabilizes everything inside it, including the solar system itself. Every orbit, from the path of the Sun around the galactic center to the movement of distant globular clusters, is shaped by its invisible pull. Scientists think that dark matter is made of exotic particles unlike anything we have yet been able to detect directly. These particles do not interact with light or with ordinary matter in the usual way. They respond only to gravity and perhaps to the weak nuclear force. Because of this, dark matter does not collide or clump together like normal matter does. It passes through stars, planets, and even our own bodies without leaving a trace. Several theories suggest possible candidates for what dark matter might be. One idea involves weakly interacting massive particles, often called WIMPs. Another proposes axions, very light particles that might fill space like a faint invisible fog. However, despite decades of research and countless experiments deep underground and in space, no one has yet directly detected these mysterious particles. Their true nature remains one of the greatest unsolved mysteries in modern science. Even though the dark matter halo is invisible, its effects are everywhere. It governs the motions of stars in both the thin and thick disks, influences the orbits of globular clusters in the galactic halo, and controls the trajectories of small satellite galaxies that orbit the Milky Way. These satellites, such as the Large and Small Magellanic Clouds, dance around our galaxy under the powerful gravitational influence of dark matter. The halo also ensures that as the Sun and its planets travel through the Milky Way, oscillating gently above and below the galactic plane in a slow, wave-like motion that takes tens of millions of years to complete, they remain securely bound to the galaxy. Without the gravitational pull of dark matter, the solar system could drift away into the dark emptiness of intergalactic space. Although the dark matter halo is not made of ordinary matter, it still interacts indirectly with the Milky Way's visible components. Its gravity shapes the long, delicate streams of stars that form when small galaxies or globular clusters are torn apart by tidal forces. These stellar streams wind around the Milky Way like ghostly ribbons, tracing the shape of the halo itself. By studying how these streams move, astronomers can map the distribution of dark matter. The paths of these disrupted stars act like fingerprints, revealing the invisible structure that guides their motion. Through detailed measurements, scientists have found that the dark matter halo is mostly spherical, though it may be slightly flattened along the plane of the galaxy due to gravitational interactions with the disk. These observations help refine models of how galaxies form and evolve, and give important clues about the nature of dark matter. The influence of the dark matter halo extends across every scale of the Milky Way. It affects the rotation curves of the galaxy, causing stars in the outer regions to orbit faster than expected. It helps keep the spiral arms stable over billions of years, preventing them from fragmenting. It influences how gas clouds and molecular clouds are distributed, and how they collapse to form new stars. Even the orbits of clusters and streams above and below the solar system are subtly guided by the unseen mass of the halo. In a very real sense, dark matter provides the backbone of the Milky Way, the invisible framework upon which all visible structures are built. Imagine standing far above the galaxy, looking down upon it from an impossible distance. You would see the glowing spiral disk, the dense bulge at the center, and the faint halo of ancient clusters around it. But beyond that, stretching in every direction, there would be an enormous invisible sphere of dark matter, extending hundreds of thousands of light years outward. This sphere would not glow or cast shadows, yet it would be there, silently holding everything in place. The Sun, the planets, the stars, and even the farthest satellites all move within its gravitational embrace. This dark matter halo not only binds the Milky Way together, but also connects it to the wider universe. Similar halos surround other galaxies, forming the cosmic scaffolding upon which the large-scale structure of the universe is built. In the grand tapestry of the cosmos, galaxies are not isolated islands of light, but are instead embedded within vast networks of dark matter filaments. These filaments stretch across space, linking galaxies and clusters together into an immense web that defines the shape of the universe itself. The Milky Way's halo is thus not just a local feature, but part of a cosmic pattern that extends across billions of light years. Understanding the dark matter halo is crucial for both galactic astronomy and cosmology. It offers clues about how galaxies form, how they evolve, and how matter behaves under the influence of gravity. The properties of the halo, its shape, density, and extent, reveal information about the earliest moments of the universe. The current structure of dark matter likely formed from tiny irregularities that arose shortly after the Big Bang, nearly 14 billion years ago. Over cosmic time, these fluctuations grew under the pull of gravity, attracting gas and dust that eventually formed stars and galaxies. In this sense, dark matter was the silent architect of the Milky Way. Without it, our galaxy, and perhaps even life itself, might never have existed. The halo's gravitational influence also has subtle effects on the solar system over immense timescales. As the Sun orbits the galactic centre, a journey that takes roughly 220 million years, it gently moves up and down through the galactic plane. This vertical motion causes it to pass through regions where the density of dark matter changes slightly. These variations, though extremely small, can influence the outermost regions of the solar system, particularly the distant reservoir of icy bodies known as the Oort cloud. Some scientists suggest that the gravitational tug of dark matter may occasionally disturb the orbits of these distant comets, sending a few inward toward the inner solar system, where they become visible in our skies. While such effects are tiny and uncertain, they remind us that the influence of dark matter reaches even into our own cosmic neighbourhood. Beyond the solar system, the dark matter halo also interacts gravitationally with small galaxies that venture close to the Milky Way. These interactions create long tidal streams of stars that stretch across the sky like luminous scars, evidence of the slow process by which our galaxy grows by absorbing smaller companions. The halo's immense gravity guides this process, determining how satellite galaxies orbit, collide, and eventually dissolve into the Milky Way's structure. Over billions of years, these interactions have helped shape the galaxy's outer regions, blending the remnants of ancient mergers into the halo we see today. Astronomers use many techniques to study this invisible structure. They observe how stars and globular clusters move, measure the bending of light from distant objects through gravitational lensing, and model the rotation of the Milky Way's disk. Each of these methods provides a different piece of the puzzle, and together they reveal a consistent picture. Dark matter dominates. Its presence is not just a small addition but the main component of the galaxy's mass. Even though we cannot see it, the motions of stars and the stability of the Milky Way confirm that this invisible halo is real and immense. Over time, as new instruments and telescopes become more precise, scientists hope to uncover more details about the halo's composition. Experiments deep underground are searching for tiny flashes of light that might occur when a dark matter particle collides with an atomic nucleus. Space missions and cosmic ray detectors are also looking for possible signals of dark matter annihilation. Although none of these efforts have yet found conclusive evidence, each attempt brings us closer to understanding one of the universe's greatest mysteries. The importance of the dark matter halo cannot be overstated. It ensures that the Milky Way's delicate balance of forces remains intact. It provides stability to the galactic disk, allowing stars and planets to orbit peacefully over billions of years. It shapes the paths of globular clusters, guides the motion of satellite galaxies, and controls the overall mass distribution of the entire system. Every star that twinkles in the sky owes its place to the unseen grip of this mysterious halo. If dark matter were to suddenly vanish, the effects would be catastrophic. The outer stars of the Milky Way would immediately begin to drift away into intergalactic space. The spiral arms would lose their structure, and the galaxy would slowly dissolve. The balance that allows gas clouds to form new stars would be destroyed. The Sun and its planets would no longer follow the same secure orbit around the galactic centre. The Milky Way, as we know it, would cease to exist. Fortunately, dark matter is not going anywhere. It has been with our galaxy since its formation, and will remain long after the last star is burned out. In many ways, the dark matter halo is a reminder of how much of the universe remains hidden from us. The beauty of the Milky Way that we see, the bright core, the graceful spiral arms, and the countless stars scattered across the sky, represents only a small portion of what truly exists. Beneath that beauty lies an invisible foundation, more massive and more mysterious than anything we can see. It reminds us that our understanding of the cosmos is still incomplete, that the greatest portion of reality lies beyond the reach of light. As the Milky Way continues its slow rotation, Completing one grand turn every few 100 million years, the dark matter halo remains steadfast and silent, guiding the motions of everything within it. Its gravitational presence shapes not just our galaxy, but also the behavior of nearby galaxies within the local group. The orbits of the Andromeda Galaxy, the Triangulum Galaxy, and numerous smaller companions are influenced by the vast halo of dark matter that extends from each of them. Together, these halos weave a gravitational web that binds the local universe. Ultimately, the study of the dark matter halo touches the deepest questions of existence. What is the universe made of? How did it form? Why does it look the way it does? The answers to these questions depend on understanding this unseen substance that fills the cosmos. Though it is invisible, dark matter defines the shape and fate of galaxies, clusters, and perhaps the universe itself. Every star that shines, every planet that orbits, and every galaxy that drifts through space does so within the gravitational embrace of dark matter. Above and below the solar system, beyond the reach of any telescope, the dark matter halo surrounds us. It does not glow, yet it holds the Milky Way together. It does not collide, yet it shapes the orbits of stars and worlds. It cannot be seen, yet it dominates everything that can be. It is the quiet architect of our galaxy, the hidden force that keeps the cosmic order intact.